This lesson's about the greenhouse effect, and here are the objectives. Now, this diagram shows the sun and the earth, and this is meant to denote the atmosphere here. In order to understand the greenhouse effect, we have to understand a few basic physical principles. First of all, electromagnetic radiation, EM radiation, is what we perceive with the human eye as light, but we can only perceive certain wavelengths of electromagnetic radiation as light, and some we can't. For example, we can't see UV light, and we can't see infrared radiation. Now, the wavelength and frequency of the electromagnetic radiation, or the light, that an object emits depends on its temperature. Hotter objects emit shorter wavelength and higher frequency electromagnetic radiation or light, and cooler objects emit longer wavelength and lower frequency electromagnetic radiation. And this also corresponds to the energy. The energy is proportional to the frequency, so shorter, higher frequency electromagnetic radiation is higher energy, and conversely, lower frequency light or lower frequency electromagnetic radiation is lower energy. Now, the sun obviously is a lot hotter than the earth, but they're both emitting electromagnetic radiation, or if we want to call it light for shorthand, we can call it that. But the sun is going to emit short wavelength, high frequency, high energy light, and that's going to be visible light primarily and UV light. Whereas the Earth, because it has a temperature above absolute zero, and everything above absolute zero, which is to say everything emits electromagnetic radiation, emits light, the Earth is also going to be emitting electromagnetic radiation, but it's going to be doing so in the longer infrared wavelengths. So this is infrared radiation. So let's go through this process from the start. The sun emits short wavelength light that travels towards the Earth. Some of that is going to be reflected by the atmosphere and clouds and things like that, and go back into space, and some is going to be transmitted towards the Earth. Now at the Earth, some of it is going to be reflected off the Earth as well, and can travel back through the atmosphere and into space. And it can travel through the atmosphere because the atmosphere is relatively transparent to this shorter wavelength, higher frequency light. However, because the radiation carries energy, that energy gets transmitted to the Earth, and that warms the Earth. Now, the warm Earth emits radiation itself. It's going to radiate energy back out into space. But because it's at a cooler temperature, the Earth is a lot cooler than the sun, it is emitting longer wavelength, lower frequency, lower energy light. And that's this infrared radiation that we're seeing here. It turns out that the atmosphere is not transparent to this longer wavelength light in the same way it was to the shorter wavelength light. And that's because the frequency of this longer wavelength light is just right to make molecules, gas molecules in the atmosphere vibrate, and when they do that, they can absorb that light. And then they re-emit it, but they re-emit it in all directions. So some's going to travel along in the atmosphere, some's going to come back towards the Earth, and some's going to go out into space. And because that energy is not just going straight out into space, but is getting radiated in all these directions, some of it coming back into Earth, the atmosphere and the gases within it, by absorbing and re-emitting this longer wavelength light, form a kind of a blanket keeping the energy in and warming the Earth. And that's how we get the greenhouse effect. Let's look at a simulation to unpack this a little further. This is the molecules and light simulation from PhET, and you can see the URL here at the top. Here I have a molecule of gas, and I can change that molecule here on the right-hand side. And here I have a flashlight. When I turn that on, it's going to emit photons of light, and I've set it to emit visible light, towards this gas molecule. And you can imagine this nitrogen molecule as being a molecule in our atmosphere. In fact, Earth's atmosphere is mostly nitrogen. So if this is the sun emitting visible light, and this is the Earth's atmosphere, you can imagine the Earth being over here, and the visible light is getting through. And that stays the same whether I choose oxygen or carbon dioxide, methane, water vapor, etc. So the atmosphere is transparent to this visible light. Now, if I go to carbon dioxide and I change to infrared light, now you can imagine this as being the Earth that's emitting this longer wavelength, lower frequency infrared light, and so now outer space is over here, and you can see that the carbon dioxide molecules are sometimes absorbing the photons of infrared light and then re-emitting them in random directions. And so only some of it is escaping to outer space, and in fact some of it is being radiated back towards the Earth over here. And so that's how these greenhouse gases like carbon dioxide and methane and water vapor and nitrogen dioxide can act as a kind of blanket. They create the greenhouse effect by re-emitting these photons of longer wavelength light back towards the Earth. Just a note before we leave this, that nitrogen and oxygen are not greenhouse gases because they are effectively transparent to infrared light as well. So nitrogen and oxygen don't absorb the infrared light, but carbon dioxide and methane and water vapor and nitrogen dioxide all absorb that infrared light. They're all greenhouse gases. So now we've seen in the simulation the gases that absorb and then re-radiate this longer wavelength energy. And those greenhouse gases that we saw in the simulation were carbon dioxide, water vapor, methane, nitrous oxide, and one that's not in the simulation but is important are fluorinated gases. Now, just to mention that the greenhouse effect is important and would exist without humans, and without it, the temperature of the Earth would be much colder. But it's the additional anthropogenic or human-created greenhouse effect that is leading to a changing climate. And that anthropogenic or human-created greenhouse effect is as a result of the emission of these greenhouse gases from human activities. So let's talk about where these come from. Carbon dioxide comes from burning fossil fuels, and that's done for energy for transport and for electricity and for other purposes. Water vapor comes from evaporation, and so there's a bit of a positive feedback effect here in that if you have more warming, you'll have more evaporation and then more water vapor, which will lead to more warming. Methane, CH4, comes largely from agriculture, from livestock, and is also the major component of natural gas and is released from industry as well. Nitrous oxide also largely comes from agriculture in the form of fertilizers. It's released when fertilizers are used in large quantities, and fluorinated gases are used as refrigerants and in industry. So the release of these gases as a result of human activities is what's leading to the anthropogenic greenhouse effect. Now, how much a particular gas contributes to the greenhouse effect depends on its concentration in the atmosphere and also on how long it persists in the atmosphere. And thirdly, on how effective it is at absorbing long-wave radiation. As we saw, different molecules have different effectiveness at absorbing different kinds of radiation. So just to give an example, if we compare carbon dioxide and methane, carbon dioxide is present in the atmosphere in a much higher concentration, and a molecule of carbon dioxide also persists in the atmosphere much, much longer than a molecule of methane. But a molecule of methane is a much more potent absorber of long-wave radiation than that of carbon dioxide. So the effects depend on all three of these things. So human activities that increase the concentration of these greenhouse gases increase the trapping of that radiation in the Earth's atmosphere and warm the Earth. And here you can see a graph of the gray line is carbon dioxide concentrations in parts per million from 1880 to 2020, and then the blue and the red is showing the difference from the 20th century average temperature. So the 20th century is going to start there and is going to end there, and so here is the average temperature over that whole time. And you can see that the temperatures are getting steadily warmer. Now, that doesn't mean that every year is hotter than the one before it. Here's a warmer year and then here's a cooler year right after. But the overall trend, as you can see quite clearly here, is that the Earth's surface temperature is getting warmer as the effect of these greenhouse gases is felt. The effects of this changing temperature are seen in heat waves, and changes in temperature also affect precipitation, so we can see droughts, and associated with droughts we get an increase in the number and severity of wildfires, and conversely we get an increase in severity and frequency of storms and flooding that's associated with that. As well, we get sea level rise as the polar ice caps melt and dump water into the ocean, and that can lead to flooding of coastal areas. So that's a look at the greenhouse effect, how humans are increasing it through the emission of greenhouse gases, and some of the effects.